which will be made by Moslehian Mohammad Sal, and titled The Recent Developments of the Gross Type Inequalities for Positive Linear Maps. Please.
First, I would like to thank the organizer for inviting me to attend this conference. My talk is about recent developments of gross type inequalities, in particular those related to positive linear maps on C-star algebra. Whenever we see a result concerning the real or complex numbers, a nice question is to ask ourselves whether it is true for example, bundle linear operators on a Hilbert space or their norms. The first version is called commutative version, and the second is called non-commutative case. This fact is based on the fact that self-adjoint operators are in fact can be regarded as a generalization of real numbers. Let me first introduce some notation. Let BH denote the C-star algebra of all bundle linear operators acting on a Hilbert space. The unit element of BH is denoted by I throughout my talk, and also this shows the usual operator norm on BH. We identify B of Cn with the algebra Mn of all complex n times n matrices in a usual manner. And we denote by BH sub H the set of all self-adjoint operators. And an operator is called positive if this inner product is greater than or equal to 0 for all x in H. In the case that A is positive and invertible, we say that it is strictly positive, and we denote it by this notation. We also denote by BH plus the set of positive operators. So BH plus positive operators, BH sub H self-adjoint operators. This denotes the operator norm. There are some analogies and differences between complex numbers and also Hilbert space operators. In my previous slides, I explained that we can try to find some generalization of some classical numerical inequalities to operators acting on Hilbert spaces. For example, we have conjugation here, and we have the Cartesian decomposition here for operators, in which A and B are self-adjoint operators. In fact, we can understand the real numbers are in fact all complex numbers satisfying this. So we may try to define self-adjoint operators by this. In fact, the adjoint is corresponding to the conjugation in the complex numbers. And also pure imaginary numbers are correspond to skew Hermitian operators. There are several differences between numbers and operators. For example, here we can see R is closed under the multiplication, but when we consider BHH, the self-adjoint operators, this set is not closed under the multiplication. For example, these operators are self-adjoint, but the product of TS is not self-adjoint. We have some other similarities. For example, here we can define positive numbers as those complex numbers satisfying this. So similarly, we can define positive operators by this. We know this is a similarity. We know R2 is positive when R is an arbitrary number. Similarly, we know when T is a self-adjoint operator, T2 is also positive. We can define an order on BHH, self-adjoint operators, like real numbers. But some facts related to real numbers is not true for self-adjoint operators. For example, when R is a number, we know one of them is true, while we have this operator, neither T is greater than 0 nor minus T is greater than 0. We can define similar to the complex number on the unit circle by unitary operators. Also, we have here the polar decomposition, and we have polar decomposition here, but instead of this complex number of the modulus 1, we have a partial isometry here. The partial isometry is an operator satisfying this equality. As we have numbers on the unit circle can be represented of this form. Also, any unitary can be represented of this form under some condition. For example, the spectrum of U should not be whole the unit circle. As I told, some inequalities concerning real numbers can be translated to inequalities for operators. For example, this is true for real numbers when alpha is arbitrary positive number, while this is true only for alpha between 0 and 1. If you take an alpha greater than 1, then you can find two operators T and S satisfying this, while this does not hold. Also, we can take a square from this, while this square is not permitted here. And also, we have similar relation here. We can define the absolute value of a complex number by this, and similarly for operators. While we have this inequality between real numbers, we can see this, if T is between minus and S, then we cannot conclude in general this inequality. And this is a counterexample for this fact. The most important is that the triangle inequality and its versions are not satisfied in general for operators. For example, here you can see we have this for positive numbers, while we cannot conclude this. But if A and B are matrices, then we can conclude this for norm of operators. Anyhow, let me start my main result by introduce some notation. A map between two CSR algebras A and B is called positive if it takes positive elements to positive elements. It is called unital when it preserves the unit of our CSR algebra. 1 is taken to 1. If we have a map, not necessarily linear, if we have a map phi, then we can define phi n from Mn of A to Mn of B. Mn of A is the CSR algebra, or the set of all matrices with entries taken from our CSR algebra. So if we have a map phi from A to B, we can define phi n from Mn of A to Mn of B in a natural way. It takes this matrix to matrix phi of Aig. In general, this map is when phi is bounded, phi n is also bounded. But in general, we do not have an upper bound for all phi n. I mean, norm of phi n is less than or equal m sub n. But maybe the supremum of mn does not exist. So if this happens, then we say that phi is completely positive, completely bounded. And phi is called completely positive if all of phi n are positive. The gross inequality states that if we have two integrable real functions f and g, under some conditions on f and g, if f and g are bounded from below and also from above, then we have this inequality. We are interested to generalize this. Not only it helps us to extend our knowledge about the structure of CSR algebra and also the geometry of CSR algebras, but also it, in fact, generalized some known results, as I will explain. Before that, let me introduce the unit orbit.
Can you be on the last slide for half a minute more?
Here we have, in fact, absolute value in general, but
Excuse me, why 1/4 is best possible? So this is not,
1/4 is here.
yes. So,
It's a precise constant.
Phi
for us.
minus b and gamma minus gamma is here. 1/4 is sharp.
for example, I will take smaller constant. What it will be?
No, for all f and g, for all f and g,
Uh-huh.
we have this. If we, maybe for some functions you can find, for
No.
some special functions you can find, but in general, this inequality holds for all f and g, arbitrary f and g. The unit orbit of an operator A is defined the set of all operators of this form, in which U is a unitary operator. It can be shown that the diameter of unitary orbit, the diameter of this set of operators, is in fact this, and also this, in which delta of A and C denotes the infimum over all lambda of norm of A minus lambda. Bartio and Davis showed that if phi is any positive unit of linear map between CSR algebras and A is between M and M, then we have this inequality, and this in fact is a reverse of the Cartesian inequality, since we know phi of A2 is less than or equal phi of A2. The speaker and Raina,
Mohammed, may you keep the previous slide? What is M and N? Is it dimension of matrices or what is on
no,
the right side?
No. You mean M and M? No.
Yes.
A is between A.
The estimates.
Yes.
Yeah.
We generalize the inequality 1. This is for any positive unit or linear map between C star algebras, but we generalize 1 for any positive linear map for n greater than 0 is 3, and for n greater than 2, we gave a counterexample that this does not hold. So we can, in fact, we have this inequality in which we have the diameter of the unit orbit here. In addition, we show that if A and B are K by K matrices, then we have this inequality for trace. Trace is, in fact, a positive linear map from MKC, MK, K by K matrices to the complex numbers. So this is, in fact, a special case of ours. Gauss inequality was generalized in the setting of inner product spaces by Sever-Dragomir and in the framework of inner product modulus on H-star algebras and C-star algebras by Ilisevich. We gave several Gauss type inequalities for unital, completely positive linear maps and unitarily invariant norms. In fact, we show that if A is a finite dimension of C-star algebra of dimension K, and phi is a unital completely positive map, then we have this inequality for all A and this for all A and B. To prove this, we use this inequality. To continue our talk, we need more notation. Let lambda 1 up to lambda n denote the eigenvalues of a compact operator A. We know the set of compact operators are countable. We denote by SJA the singular values of A, and singular values of A, in fact, are the eigenvalues of the absolute value of A. By a unitary invariant norm, we mean a norm on a two-sided ideal of KH satisfying this equality for all unitaries U and V and all A in our norm ideal. An example of unitary invariant norm is the operator norm, and another important class of unitary invariant norm are Schatten classes. It is the set of all compact operators for which this series is convergent. Here we have the singular value of A.
What do you mean under norm ideal? Norm ideal?
Yes, it is called norm ideal since it is an ideal under this norm.
Under this norm?
This norm,
okay.
yes.
You define it so?
Yes. As a consequence, we get this inequality of Gauss type in which we have a unital completely positive map phi. Then we can show that this holds. Here is the diameter of the unit order, the set of all U star AU. The diameter of this set of operators is denoted by dA. And as a consequence, we show that, in fact, this inequality holds in which we have Schatten P norm here for all A and B in MM. It's clear that in the case that